Gravity is one of the most misunderstood concepts in physics, and Richard Feynman often pointed out that people get it completely wrong. Most of us imagine gravity as a simple force that pulls objects downward. Yet what we truly feel when standing on the ground is not a pull from the earth, but the push of the ground against us. Isaac Newton's law of universal gravitation accurately describes how objects attract each other, but it does not explain why this attraction occurs. Albert Einstein revolutionized our understanding by showing that massive objects curve the fabric of space-time, and that what we call gravity is actually the motion of objects following the natural curves of this geometry. Feynman emphasized that simple analogies like apples falling or magnets pulling mislead our intuition. The real beauty of gravity lies in its subtlety. It is geometry in motion, not an invisible string. By understanding this, we can correct old misconceptions, appreciate the elegance of Einstein's equations, and glimpse the deeper mysteries of the universe. Physics shows that even though we live in a world dominated by gravity, our senses and early education often fail to reveal its true nature. Observing the motions of planets, satellites, or free-falling objects demonstrates how space and time themselves guide the paths of matter. Feynman's lectures often reminded students that questioning assumptions is as important as learning formulas. Science thrives on curiosity, and gravity is a perfect example of how reality can surprise our intuition. To go even deeper into this idea, we must begin to shift our perspective away from thinking about gravity as a force, and instead start thinking about motion through curved space-time. This change in viewpoint is not just a small adjustment. It is a complete transformation in how we understand the universe. When we see a planet orbiting a star, it may appear as though the star is pulling the planet inward with some invisible force. However, according to Albert Einstein, this is not what is truly happening. The planet is actually moving along the straightest possible path within a curved space-time geometry. This path is called a geodesic, and it represents the natural motion of an object when no external forces interfere with it. In this sense, gravity is not something that pulls objects off their path. Instead, it defines the very paths that objects naturally follow. What we perceive as attraction is actually the result of objects moving through a geometry that has been shaped by mass and energy. This idea may feel strange at first, because our everyday experiences teach us to think in terms of pushes and pulls. However, once we begin to see gravity as geometry rather than force, many puzzling phenomena start to make much more sense. To help build some intuition, imagine placing a heavy ball on a stretched rubber sheet. The weight of the ball causes the sheet to dip, creating a curved surface. If you then place a smaller ball nearby, it will roll toward the heavier one. At first glance, it might seem as though the larger ball is pulling the smaller one. In reality, the smaller ball is simply following the curved surface created by the heavier ball. While this analogy is not perfect, it offers a useful way to begin visualizing how mass can influence the structure of space-time. However, as Richard Feynman often pointed out, analogies like this can only take us so far. The real structure of space-time is far more complex than a two-dimensional sheet. In reality, we are dealing with 4 dimensions, 3 of space and 1 of time, all woven together into a single fabric. This fabric can stretch, bend, and warp in ways that are difficult to fully imagine. Because of this, our intuition, which is based on everyday experiences in a mostly flat and slow-moving world, often fails us. When we try to understand gravity at a deeper level, one of the most fascinating consequences of this understanding is that time itself is affected by gravity. Time is not constant or universal in the way we once believed. Instead, it flows at different rates, depending on the strength of the gravitational field. This phenomenon is known as gravitational time dilation. Near a massive object, such as a planet or a black hole, time passes more slowly compared to regions with weaker gravity. This is not just a theoretical prediction. It has been tested and confirmed through precise experiments. For example, highly accurate atomic clocks placed at different altitudes on Earth will tick at slightly different rates. Even more importantly, the satellites used in global positioning systems must account for these differences. If they did not, the system would quickly become inaccurate, and navigation would fail. This shows that gravity is not only about motion through space, but also about the flow of time itself. Another powerful way to understand gravity is by observing objects in free fall. When something is falling freely under the influence of gravity, it is actually following its natural path through space-time. There is no force acting on it in the traditional sense. In fact, from the perspective of the falling object, it feels as though there is no gravity at all. This is why astronauts orbiting Earth experience weightlessness. They are not beyond the reach of gravity. Instead, they are constantly falling toward Earth, but their sideways motion keeps them in orbit. What we commonly experience as weight is not caused by gravity itself. Instead, it is the result of resistance to gravity. When you stand on the ground, your body is prevented from following its natural path through space-time. The ground pushes up against your feet, creating the sensation of weight. This is a subtle but profound shift in understanding. It means that what we feel is not gravity pulling us down, but the ground pushing us up. Isaac Newton provided a mathematical framework that allowed scientists to predict the motion of objects with remarkable accuracy. His laws of motion and universal gravitation remain incredibly useful even today. They work extremely well for most everyday situations and many engineering applications. However, they do not explain the deeper nature of gravity. They describe how gravity behaves, but not why it behaves that way. Einstein's theory of general relativity goes further by explaining gravity as the curvature of space-time itself. It does not replace Newton's theory entirely, but rather extends it. In situations involving very strong gravitational fields or very high speeds, Einstein's equations provide a more accurate description. This relationship between the two theories is an important reminder that scientific knowledge evolves over time. Each new theory builds upon the successes of previous ones, while also revealing new layers of understanding. Another remarkable prediction of general relativity is the bending of light by gravity. According to this theory, light does not always travel in straight lines. When it passes near a massive object, its path curves along with the space-time around it. This effect, known as gravitational lensing, has been observed many times by astronomers. It allows scientists to detect distant galaxies and study massive objects that would otherwise remain hidden. Gravitational lensing also provides strong evidence for the existence of dark matter. In many cases, the amount of bending observed cannot be explained by visible matter alone. This suggests that there is additional mass present that we cannot directly see. Once again, gravity reveals itself as a powerful tool for exploring the unseen aspects of the universe. Perhaps the most extreme examples of gravity are black holes. These objects are formed when a massive star collapses under its own gravity. The result is a region of space, where the curvature of space-time becomes incredibly intense. At a certain boundary, known as the event horizon, the escape velocity exceeds the speed of light. This means that nothing, not even light, can escape once it crosses this boundary. Inside a black hole, our current understanding of physics begins to break down. The equations of general relativity predict a singularity, a point where density becomes infinite, and the known laws of physics no longer apply. This suggests that our theories are incomplete, and that a deeper understanding is still needed. Scientists continue to search for a theory that can unify general relativity with quantum mechanics, which governs the behavior of particles at the smallest scales. This search for a unified theory is one of the greatest challenges in modern physics. It requires us to rethink our assumptions and explore entirely new ways of describing reality. Some approaches, such as string theory and loop quantum gravity, attempt to bridge this gap. While these ideas are still being developed, they represent exciting possibilities for the future of science. Throughout all of this, Richard Feynman consistently reminded us that the goal of science is not simply to memorize formulas or accept explanations without question. True understanding comes from curiosity, skepticism, and a willingness to challenge our own assumptions. Gravity serves as a perfect example of this principle. It is something we experience every day, yet its true nature is far more subtle and complex than it appears. As we continue to explore the universe, new discoveries will likely deepen our understanding of gravity even further. Observations of gravitational waves, for example, have opened a new window into the cosmos. These ripples in space-time are produced by massive objects, such as merging black holes or neutron stars. Detecting them allows us to study events that would otherwise be invisible. Gravity also plays a crucial role in shaping the large-scale structure of the universe. It governs the formation of galaxies, the motion of stars, and the evolution of cosmic structures over billions of years. Without gravity, the universe would not have the complexity and richness that we observe today. It is both a guiding force and a geometric framework that connects everything, teaches us an important lesson about the nature of reality together. In the end, gravity teaches us an important lesson about the nature of reality. What seems simple at first can turn out to be deeply complex when examined more closely. Our senses and everyday experiences provide only a limited view of the world. To truly understand the universe, we must go beyond intuition and rely on careful observation, mathematical reasoning, and open-minded exploration. As Albert Einstein showed through his work, the universe is not only more complex than we imagine, but often more surprising as well. By embracing curiosity and continuing to ask questions, we move closer to uncovering the deeper truths that govern existence. Gravity, in all its subtlety and elegance, remains one of the most powerful reminders that reality is far richer than it first appears.